Right. So in this video, I want to discuss the design of scan heads in order to focus a particular beam on a working surface. For this purpose, we would compute the spot size as well as the working area for various scan heads that are given in this table right here. I would discuss them later, but initially we would discuss the spot size and working area, followed by the design of a refocusing lens in order to improve the final spot size for any beam. Because whenever we have a beam and we have a working area, we kind of want to control that beam on the working area such that it transfers the maximum energy and there is minimum loss, um, and and to basically focus the beam as effectively as possible. In order to do that, various lenses are used, which are usually referred to as scan heads, which are the direction or the orientation of which are controlled by usually two orthogonal mirrors on x and y axis, which are also called galvanomirrors. And these scanners are usually use f theta lens. So f theta lens are not normal lens in the senses that they ensure a linear relation between the angle of incidence as well as the displacement compared to the spherical lenses, which basically curves the working surface, as we will see later. So first of all, we would consider f theta lens in order to do our analysis for the given spot sizes, and in order to compute the spot sizes with the given initial beam waist and the apertures, and then we would look at the design of the pre-focusing lens. So in this first part, let us compute the spot size and the working area for various scan heads. In order to do that, we have to define the truncation for our scan head lens. And truncation factor is basically decides the power loss as the beam is going to pass through the lens. And a good considerable ratio is between 0.7 to 1, where 1 corresponds to no power loss at all. So if we consider that usually or I should say real truncation that is usually found in f theta lens, it's around zero point 0.7. So we proceed analysis with the truncation factor of zero point 0.7, which corresponds to the power loss of 1.68%, which is almost negligible. Once we have the power loss and the truncation, we can then find the beam diameter by multiplying the truncation with the diameter of the lens itself, which is given here in this formula, and the initial spot size is essentially given as the half of the beam diameter, which is dB over 2. And then similarly, with the initial spot size, we can find the Rayleigh range ZR, as seen here, which is essentially the square root 2 times the beam waist, the distance at which the beam waist basically reduced by the factor of square root 2. And once we have the Rayleigh range, we can finally find the final spot size given by omega 1 on the working surface. Further, these relations can be used to find the numerical aperture as well as the deflection angle theta in the analysis follow. This M2 factor can also be found with the numerical aperture and the previously found factors of initial spot size and the beam wavelength. Right, so for the working area, we know that since we have two reflection mirrors given by the galvanomirrors of x and y, we can simply multiply the focal length with the tangent of twice the maximum degree of deflection, which is about 15 degrees, which will correspond to the working area. So for these particular lens, given we are given their particular wavelength as well as M2 factor for the first two, and for the second one, we are given the wavelength along with the numerical aperture. From numerical aperture, we can find the M2 factor, and corresponding to these and the scan heads and the focal lengths, we can find the spot size as well as the working area. Working area, as we see, can be found using this relation, and spot size, as we see, can be found using this relation of omega 1 right here. So I've attached the MATLAB code here in the script that I will provide in the description, so you can run this and change the corresponding wavelengths and the focal lengths in order to do the analysis for your own scan head lenses. But for these particular lenses that are given here, the beams that are given here, we can notice that if we increase the spot size, sorry, if we increase the focal length, or the corresponding spot size also increases and corresponding working area also increases. This is because the spot size as well as the working area is directly proportional to the focal length of the particular lens. Um, for the third one, you may notice that although the focal length is lesser than the first two, but the spot size is greater. It's because the M2 factor is quite high, and due to which the beam basically diverges instead of converging to a smaller uh, smaller region basically. Right. So for the second part, so this one falls for the f theta lens, followed by the second analysis, which is for the spherical lens, in which we substitute the f theta lens with the spherical lens. So previously, our assumption, the f theta lens was assuming that the entire work is the spot size on the entire working space would remain same. But when we are talking about spherical lenses, the spot size tends to change its diameter as we move across the working space, and that change is given by the factor of cos theta. Cos theta compared to which basically is opposite to having a linear relation between the displacement and the angle of incidence. And this particular from this particular contour plot, you can see that on the entire working area given by the x and y mirrors, we can see that the spot size tends to change as we move away from the center. In the center, as you can see, the spot size is minimum, which is about 20.8 micrometer. But as we continue to move away from the center, for example, if we deflect our beam away from the center region of the working space, the spot size will tend to increase. As you can see here, it on the four corner edges, it goes to about 21.4 micrometer and above. Corresponding to this, you can also find uh, the, the 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 code here, the MATLAB code here, where I first declared the corresponding wavelength for the lens that for the laser that we've selected, its corresponding focal length and M2 factor, as well as scan head aperture. Then we have created the working space in this particular in these particular lines. Finally, followed by the effective focal length, which is basically divided by the factor of cos theta, as you see here. And these are the relations that we saw previously and that we have used the same way as before. And this is simply the contour plot. Again, you can change these particular values for your own lens, depending upon whatever wavelength or focal length that you decide to go for. And if we run this particular section, you can clearly see that the contour plot that we obtained earlier right here. So you can see that as we move away from the center of the working area, the spot size tends to increase. So this is the drawback of the spherical lens compared to the f theta lens, and this can be essentially this is what we want to improve in the next section, which is the design of pre-focusing lens. Essentially, what we want is that this difference of changing spot size from the compared to the center has to be minimized. And in order to do that, we design the pre-focusing lens in this particular section.